everyone. In the previous class, we were discussing about the toppling failure mode as far as rock slope stability is concerned. We saw that how we can obtain the block geometry, and then we started our discussion with block stability. Let us continue with the same discussion today and try to see that how we can find out whether the slope is safe against toppling failure or not. So, we saw this figure in the previous class. Let us try to go through it once again and try to find out that what were the salient features as far as this figure is concerned. I mentioned to you that there are three sets of blocks which can be present. These can be stable, these blocks may topple or these may slide. As far as this figure is concerned, you can see that this block and this block, they are stable blocks. However, this block and this block, these three have the tendency to topple, and the blocks, this one and this one, they are prone to sliding. And it was assumed that the moment this block at the toe, it slides, the slope is considered to be unstable. This distance which has been shown here by B is constant for all the blocks. These were the assumptions which were involved. And if you recall, we obtained the number of blocks that will be present in such type of rock slope, and that we represented as N. Here, the lower part of the slope has one slope, however, above the crest the slope is something else. So, basically it will look like this. Like this has one value and the upper portion has the other value. Then any block which is say nth block here, this nth block can be above the crest, that means in this zone. It can be just at the crest, that is here, or it can be below the crest, which is like this. So, depending upon where this nth block is located, accordingly you can obtain the block geometry as we have discussed in the previous class. Now, here you can see that for nth block, we have taken the height of the block as yn. Then, now what we will do is, we will try to have the forces which are acting on any typical nth block. Then, we will take one nth block which is having the tendency to topple, and we will take another nth block which will have the tendency to slide, and then we will try to get the force equilibrium equation and then try to see how this system can be analyzed. Take a look here. The first figure gives you the idea about the forces which are acting on the nth block. So, here you can see that these normal forces Pn and Pn minus 1, they are acting at a distance of Mn and Ln respectively from this base of the block. While these shear forces, that is Qn and Qn minus, they are acting as shown in this figure in this particular manner. This width of the block is delta x and the height is yn. This slope is given as psi p. there is going to be another force which is the normal to this block, that is given by Rn, and this is acting at a distance of Kn from this face of the block. Now take a look at the second figure in this slide. This shows the toppling of the nth block. So you can see here that there is a gap between these two planes, that shows that this nth block is going to topple. Now here you see that you have a force Rn and another force which is parallel to this base, that is Sn. Weight of the block is given by this Wn, and these forces which are Pn and Pn minus acting in this particular plane at a particular location, which has been shown in this figure and given by Mn and Ln respectively. Now if this nth block does not topple but it slides, then in that case you see that there is no gap here in between these two planes, and this block is going to only slide. Weight is again Wn, this normal force is Rn, and base friction angle is phi b, and therefore this tangential component which will be perpendicular to this normal force, that is going to be Rn tan phi b, and the forces Pn and Pn minus 1 are shown like this. Similarly, Qn and Qn minus 1, which are the shear forces at that block in this direction, has been shown here in this particular figure. Now let us consider a typical nth block. So the normal and the shear forces that are developed on the base, I mentioned to you that these are Rn and Sn, and at the interfaces with the adjacent blocks, like has been shown here, normal forces are Pn and Pn minus 1, and the shear forces are Qn and Qn minus 1. So these are the typical forces which are acting on the nth block. Now let us first take a block which is belonging to the toppling set. So in that case, point of application of all the forces are known, like here you can see Mn and Ln, they are known, where the Pn and Pn minus 1 respectively, they are acting. So this is the figure again showing the toppling of the nth block, and then these forces are there, Rn and Sn and Pn and Pn minus 1, and here you have Qn and Qn minus 1, which have been represented in terms of Pn and phi d. Now in case of these toppling block, the points of application of the normal forces Pn, these are given as Mn and Ln, we have seen in the previous figure, on the upper and lower faces respectively. See here, this Pn is acting at a height of Mn and Pn minus 1 is acting at a height of Ln. Now I take the three cases, that is whether this nth block is above the crest, at the crest, or below the crest of the slope. So there is going to be three cases. If nth block is below the slope crest. What will happen in that case? Your Mn will become equal to Yn. Make it equation number 13. Till equation 12 we have in previous class, and Ln will be equal to Yn minus A1. That is equation number 14. Now, if this nth block is the crest block itself, then in that case Mn is going to be Yn minus A2. This will be equation number 15, and Ln will be Yn minus A1. This is equation number 16. And then we will have the third case where you will have if this nth block is above the crest. Then in this case what will happen? This Mn will become equal to Yn minus A2 and Ln is equal to Yn. What are these A1, A2? Everything you have with you, and you can refer to the first figure of this lecture which I have already shown it to you. Now, in case of sliding and toppling, frictional forces are generated on the bases as well as on the sides of the blocks. In many geological environments, the friction angles on these two surfaces are going to be different. For example, if you take the steeply dipping sedimentary sequence which is comprising of sandstone beds and separated by thin seams of shale. So, in this case what will happen is that the shale will form the sides of the blocks, while the joints in the sandstone will form the bases of the blocks. And the moment the material at the base of the block and the side of the block is different, most likely the friction angles will also be different on these two surfaces. So, for such type of conditions, the friction angle of the sides of the blocks is being represented by phi d. This will be lower than the friction angle on the base, which is phi p. Now, these two friction angles can be incorporated into the limit equilibrium analysis as we are going to discuss. So, for the limiting friction on the sides of the block, we can write that Qn is equal to Pn tan of phi d. Take a look here, this is your Pn and here the friction angle is phi d. So, this Qn will be Pn tan of phi d. So, this equation will be 19, and similarly you can write Qn minus 1 as Pn minus 1 tan of phi d. This will be equation number 20. Now, by resolving the perpendicular and parallel to the base of a block with weight Wn, the normal and the shear force which will be acting at the base of the block, they can be obtained as Rn equal to Wn cos of psi p plus Pn minus Pn minus 1 tan of phi d. Equation number 21. And then if you take the shear force, it will be Sn equal to Wn sin psi p plus Pn minus Pn minus 1. So, there is nothing difficult. Take a look at this figure and then get the force equilibrium in the direction perpendicular and parallel to the base of the block whose weight is given by Wn. Then we take the rotational equilibrium and we try to find out this force Pn minus 1, which is just sufficient to prevent toppling. How to do that? Take a look. So, you see that I take the rotation at this point. So, the first force is going to be Pn minus 1 comma t. Why I write t is because I am dealing with the toppling. This at what distance that it is acting? Ln. So, this multiplied by ln, and what is going to be its direction? About this point, this is going to be in this direction. That is the clockwise direction. This is going to be equal to, see this Pn is there and it is acting at this distance of Mn, and when it creates the rotation, it is going to be Pn into Mn and it will be in the anticlockwise direction. So, this is how we are going to write Pn into Mn and it is going to be in this direction. Then this weight component which is there, so you will have these two weight components, one like this and another one like this. So, the one component is going to give me, that is Wn cos of psi p, and where is this acting? This distance is delta x, so this is going to be delta x upon 2. So, this is going to be delta x upon 2 and this is going to cause the moment in the clockwise direction, and then you will have another component of W which is Wn sine of psi p, and this is acting at a height of this yn upon 2. So, this is going to be yn upon 2 and its direction will be this, and then you will have the last component which is this Pn tan of phi d. So, that would be Pn tan phi d multiplied by delta x. What about this Pn minus 1 tan phi d? Because it is passing from this, so it will not have any kind of rotational moment there. So, this is what is going to be in this direction. So, you can write this Pn minus 1 comma t is equal to Pn into Mn minus delta x tan of phi d plus Wn upon 2 multiplied by yn sine psi p, which is this term, minus delta x cos of psi p. So, this whole thing in a box bracket and this divided by ln. Make this equation as equation number 23. Take a note of these equation numbers because we will be referring these later when I will be summarizing the steps for the analysis in case of the toppling failure that we are taking up right now. So, for the block which is belonging to the sliding set, so till now what we discussed about the toppling block, but then in case if the nth block is not toppling but undergoing the sliding, then what can be the situation. So, here are the forces which have been shown in case of the sliding of the nth block. So, what we are going to get here as Sn will be equal to Rn tan of phi p, that is equation number 24, and the magnitude of the forces, that is Qn minus 1, Pn minus 1 and Rn, and their points of application, which are Ln and Kn. You can see here this is what is your Kn and these are Ln's. So, these are unknown. The question is, if all these are unknown, how we will get the solution? So, this is a kind of indeterminate problem. In order to make it determinate, we need to have some kind of an assumption. So, the assumption which is involved here is that force Pn minus 1, which is required to prevent the sliding of nth block, is determined by assuming Qn minus 1 to be equal to tan of phi d into Pn minus 1. That means it is assumed that there is the full mobilization of the strength that is going to take place, because if that full mobilization is not there, this condition will not be satisfied. So, considering this, the magnitude of Qn minus 1 would be known to us, and therefore, it will reduce some number of unknowns and the problem will become determinate. So, how to carry out the analysis? So, what we do is we resolve the forces in the direction of this Pn minus 1. So, let us do that, resolving the forces in the direction of Pn minus 1. What we will get is Pn minus 1 comma S. Why I am using S here? Because now I am taking the sliding of the nth block. So, this minus Pn plus Rn tan of phi p minus Wn sin of psi p. This is going to be equal to 0. Then what are the forces in the direction perpendicular to Pn minus 1? These are going to be Rn, which will be equal to Wn cos of psi p plus Pn minus 1 comma S into tan of phi d. So, this is what that we are going to get. Now, if we substitute this expression of Rn in this equation, what we are going to get is, so we have to substitute this Rn, what we get? It will be Pn minus 1 comma S minus Pn plus Wn cos of psi p plus Pn minus Pn minus 1 comma s into tan of phi d into tan of phi p minus Wn sin of psi p, this is equal to 0. Now you take the terms of this Pn minus 1 comma s together. So this is what that we are going to get. This will be 1 minus, and here you will have this and this. So it will be tan of phi d into tan phi p and minus Pn. Again you will have 1 minus, because I have taken the minus sign here. So here this is with the positive sign. So this will become minus. This is going to be tan of phi d tan phi p and plus I will have Wn as cos of psi p tan phi p minus sin of psi p. That is going to be equal to 0. Or we can write here as Pn minus 1 comma s is equal to Pn minus Wn cos psi p tan phi p minus sin psi p divided by what? This term, that is 1 minus tan phi d tan phi p. So this is how we will get the Pn minus 1 for the nth block which is undergoing the sliding. Make this equation as equation number 25. So now after knowing that how can we calculate this Pn minus 1 for the nth slide which is undergoing either the toppling or the sliding, let us try to see how to go ahead with the complete analysis as far as the toppling failure of the slopes are concerned. So it is the calculation procedure for toppling stability has been given here. So the first step is going to be you need to find the geometry of every block. Then values of the friction angles on the sides and base of the blocks, they are phi d and phi p. We need to assign these on the basis of lab testing or inspection at site, and you need to keep in mind that this phi d will be greater than psi p. Then we will start with the top block and identify if the toppling will occur or not. And when the toppling will occur, this condition, that is y upon delta x, has to be greater than cot of psi p will be true. This we have seen when we were discussing about the kinematic analysis of the toppling failure. Now for the upper toppling failure, just now we obtained equations 23 and 25. These would be used to calculate the lateral forces which are required to prevent the toppling and sliding respectively. So we will use these equations 23 and 25 in order to get that P n minus 1 comma t and P n minus 1 comma s. Now let us say that N1 be the uppermost block of the toppling set. Now starting with the block N1, we will determine the lateral forces P n minus 1 comma t which is required to prevent toppling and Pn minus 1 comma s to prevent the sliding. If the Pn minus 1 value for toppling works out to be more than that for the sliding, this means that the block is on the point of toppling, and Pn minus 1 would be assigned the value which is corresponding to Pn minus 1 t. So, see here what we are trying to check is, for every block I am trying to find out what is the force that is required to stop toppling and sliding both. Now, whichever is more, that mechanism is going to govern that particular block. So, in case if you have Pn minus 1 t greater than Pn minus 1 s, block is on the point of toppling, and accordingly this Pn minus 1 will take the value of Pn minus 1 corresponding to toppling, that is Pn minus 1 comma t. And in another case, if Pn minus 1 comma s is more than the toppling value of Pn minus 1, that means that the block is on the point of sliding, and your Pn minus 1 will become equal to Pn minus 1 comma s. So, this is how that for every block starting from the top, we are going to decide whether it is going to topple or slide, and then what is going to be the value of this Pn minus 1 depending upon whether the block is toppling or whether the block is sliding. In addition to this, a check needs to be made that there is a normal force R on the base of the block, and that the sliding does not occur on the base. That means that Rn has to be more than 0, and your Sn, mod of Sn, should be more than Rn tan of phi p. So, in addition to these conditions, this condition should also be satisfied. Now, the next lower block, which is N1 minus 1, and all the lower blocks, they will be treated in succession using the same procedure. So, first you take the first block which was N1, then you go to N1 minus 1, and then you try to get the Pn minus 1 value for the block N1 minus 2, and so on. It may be found that the relatively short block that does not satisfy the equation number 2 for toppling, it may still topple if the moment applied by the thrust force on the upper face is great enough to satisfy the condition that we have stated in the earlier step, which is step number 5. Now, if the condition, that is Pn minus 1 toppling, is more than Pn minus 1 sliding, is met for all the blocks. What does that mean? That the toppling extends down to block number 1 and sliding will not occur at all for all the blocks which are there on that slope. Now, eventually a block may be reached for which it can have Pn minus 1 sliding more than Pn minus 1 toppling. So, this will establish the block N2, and for this and all the lower blocks, now the critical state is going to be that of the sliding and not toppling. So, the stability of the sliding block is now going to be checked by using equation number 24, with the block being unstable if Sn is going to be equal to Rn tan of phi b. Now, if this block 1, which is the lowermost block near the toe of the slope, is stable against both sliding and toppling, that is P0. Why we are getting this P0? Because it is the block number 1, and for block number 1 Pn minus 1 will be P0. So, if P0 is less than 0, then the overall slope is going to be stable. Now, if this block 1 either topples or slides, that means if this P naught is greater than 0, then the overall slope is going to be unstable. So, this is how we can find out whether the slope is going to be stable or unstable. So, you need to go in a systematic manner starting from the topmost block and then go one by one towards the toe of the slope, and then keep finding out that what is going to be the value of Pn minus, what is going to be the value of Pn minus 1 for each of these blocks. Apply a check which one is the dominating mechanism, whether it is toppling or whether it is sliding. Accordingly, you assign the value to this force Pn minus 1, and ultimately when you carry out this analysis for the block number 1, which is the lowest block at the toe of the slope, that is going to decide whether the slope is going to be stable or not. If the bottommost one is neither sliding nor toppling, that means that the slope is going to be stable, otherwise it is unstable. If the slope works out to be unstable, you need to provide some kind of a slope stabilization measure, and in case of the toppling failure, we provide the anchor there, and with the tension that is mobilized in that anchor, that toe block gets stabilized. So, there are various ways that we can stabilize these slopes under different types of conditions. So, all these things we will take up in the next class. Thank you very much.